In this section, we're going to look at neutralization reactions. So if I have a pH scale here, and remember on the low end we have acids with high hydrogen ion concentrations, and on the high end we have bases with high hydroxide ion concentrations. And I start out with an acid, something that has a lot of hydrogen ions. If I start adding a base, what you're actually doing in the reaction is you're adding hydroxide ions, and they are taking away the hydrogen ions. As I add the base, it becomes less and less concentrated with hydrogen ions and more concentrated with hydroxide ions. If I add too much, I'll have a very high hydroxide ion concentration. So if I add more acid, I start taking away the hydroxide ions in favor of hydrogen ions. But if I add the exact same amount of hydrogen ions as I have hydroxide ions, I end up at a pH of 7, and that's neutral. So when hydrogen ion concentration equals the hydroxide ion concentration, we've undergone what's called neutralization. Anytime a hydrogen ion reacts with a hydroxide ion, we make water. And if all of the hydrogen ions are reacted with all the hydroxide ions in a 1-to-1 ratio, we make molecules of water. And there's nothing left over, and it's perfectly neutral. No acid, no base, just pure water. So here's how every neutralization reaction works. You have an acid plus a base, and you make water, but you also make a salt, because the salt comes from the other cations and anions that are in these acids and bases that aren't hydrogen or hydroxide. So every neutralization, like I said, makes a salt and a water. So here's a common neutralization reaction. We have hydrochloric acid reacting with sodium hydroxide, and it's just a double replacement reaction. The hydrogen and the sodium are going to switch places, so that's where the NaCl comes from. The Na will come over here and pair up with the Cl and make sodium chloride, and the H will come over here and pair up with the hydroxide and make HOH, which is water, H2O. So here's an example, acid-base neutralization. So this should be no problem for you. You should be able to one, recognize that it's an acid-base neutralization because you have an acid, H2SO4, sulfuric acid. It's a Arrhenius acid. It'll give off this hydrogen ion in solution, or will donate this hydrogen ion. And then you have KOH. This is a metallic hydroxide, which is a very common base. So you should be able to predict the products for this no problem. It's just a double replacement reaction. The hydrogen ion from the sulfuric acid will now partner up with the hydroxide ion from the base, and it will make water. And then the potassium ion from the base will pair up with the sulfate ion from the acid. Okay, don't forget to crisscross your charges. We'll have K2SO4, and then we need to balance. We have 2 Ks on the right, 1 on the left, so we'll put a little 2 in there, and I think that's it. Oh no, we need to put a 2 here as well to balance out the hydrogen ion. So I have 2 hydrogen ions plus these 2 is 4 hydrogen ions, so I need a 2 here to balance out and make 4 hydrogen ions. So we've made our water. I've written it as HOH, but really HOH could be rewritten as H2O. So this is my water, my product that's always the product in a neutralization reaction. And then I have K2SO4, potassium sulfate. This is a salt. This is a metal combined with a polyatomic ion acting like a nonmetal. Well, it's all nonmetals, but I have a cation and an anion, very characteristic of salts. So in summary here, acids neutralize bases and bases neutralize acids. When these substances come into contact with one another, the hydrogen ions of the acid combine with the hydroxide ions of the base. When the concentration of hydrogen ions and hydroxide ions is perfectly equal, then water is made. A salt is also produced by every neutralization reaction. And to predict this product, or all the products of any neutralization reaction, it's very simple. You should just do the double replacement, which we've already learned back in chapter 11. So these should be no issue for you.